Welcome to The Explainer. Today, we're going to dive into one of the most powerful ideas fueling modern AI. And it's an idea we borrowed from the most complex and incredible machine we know of, the human brain. It's wild to think that just a few years back, even a giant like Google's co-founder Sergey Brin basically said, for decades, everybody knew AI didn't work. And then, almost overnight, it just started working. Suddenly, computers could see cats in photos, and that one little surprise kicked off a massive revolution that's changing pretty much everything. So, what happened? What was that secret sauce? What was the breakthrough that let machines suddenly make sense of our messy, beautiful, complicated world? That's the big question we're going to tackle in this explainer. Okay, so here's our roadmap. First, we'll talk about just how sudden this AI revolution really was. Then, we're going to look at the blueprint scientists found inside our own skulls. We'll unpack this core idea of sparsity, check out the different ways AI learned using this blueprint, see it all in action, and then wrap up by asking, what does this all mean for the future of science? To really get this, you have to understand it wasn't a slow, steady improvement. No, it was like flipping a switch. For years and years, AI progress was just slow. Then, bam, machines went from being clunky calculators to things that could actually kind of perceive the world. And this leap was a genuine shock, even to the very people who had dedicated their lives to it. So, with this sudden revolution on their hands, researchers had to ask, where on earth can we find a working model of intelligence? And the answer was staring them in the mirror. It was inside our own heads. To build truly smart machines, they turned to the ultimate source of inspiration and started to reverse engineer the principles that make our own brains so unbelievably powerful. And what they found was just fascinating. It seems the brain uses this general, repeatable architecture. I know this quote here looks super technical, but what it's really saying is that the neocortex, that's the part for all our high-level thinking, it's basically a universal learning machine. It's a flexible system that can learn to process any kind of pattern, doesn't matter if it's from your eyes or your ears, and that was the key insight. If we could figure out its basic operating principles, we could build them in silicon. So what's the number one rule we learned from the brain's blueprint? Efficiency. Your brain is, in a good way, kind of lazy. It doesn't process every single pixel of light that hits your eyes. Instead, it's a master at picking out only what's important and just ignoring the rest. It's what we call a sparse system. And this slide just nails the concept. Over on the left, you've got dense information. It's just noise, it's clutter, it's a ton of work to process. Think of trying to find a face in an old TV screen full of static. That was the old way AI tried to do things. But on the right, you've got sparse information. It's just the essential features, the simple lines that tell you tree or bird. It's clean, efficient, and so much easier to understand. The big idea was realizing the brain, and the AI we built to mimic it, works on the right. And this brings us to the hero of our story, sparse coding. Now, forget that technical definition for a second, because the idea is actually beautiful. It's like teaching a computer to create its own visual alphabet. Instead of memorizing every single picture it ever sees, it learns a library of basic building blocks, edges, curves, textures. Then, to describe a brand new image, it just grabs a handful of those alphabet letters and spells it out. It's an incredibly efficient way to see the world. So how does it learn this alphabet? Well, it's a pretty cool three-step process. First, the system just looks at thousands and thousands of tiny, random snippets of images. Then, as you see in step 2, it starts to figure out the most common recurring patterns, the atoms of vision. These are the simplest things like straight lines, curves, and little gradients. And finally, once it has that dictionary, it can look at a whole new complex picture and describe it super efficiently, using just a few of those atoms it learned. And really, this slide sums it all up. The goal is to represent complex things using just a few simple building blocks. It's exactly what your brain does when you look at a face. You don't see every pore, you see the sparse features, the curve of an eyebrow, the shape of the eyes, and that's what we're teaching AI to do. Okay, so we've got an efficient, brain-like way to represent the world. You can think of that as the hardware. But how does the AI actually use all this to do something useful? Well, that's where the software comes in. Let's look at the 3 main ways these systems learn. First up, supervised learning. This is basically like studying for a test with the answer key. You show the machine thousands of cat pictures labeled cat, thousands of dog pictures labeled dog. And because it's already focused on those simple, sparse features, just the essential lines of a cat's ear or a dog's nose, it learns to tell them apart way more efficiently. Next, we've got unsupervised learning. This is where it gets really cool. This is learning by just watching. There are no labels, no answer key, This is exactly how the system built that visual alphabet we were talking about. It just looks at the world and figures out the common patterns all by itself, building its sparse dictionary from the ground up. And finally, there's reinforcement learning. This is learning by doing, classic trial and error. An AI agent, say a self-driving car, tries stuff out. When it correctly spots a stop sign using its sparse features, it gets a little digital reward. This helps it quickly learn to focus on the handful of important things in a chaotic world to get the job done. All right, so we have this brain-inspired way to see the world, and we have these powerful methods for learning. Now, let's put all the pieces together and see what kind of real-world cognitive abilities we can build. And the range of applications that come from this one blueprint is just staggering. I mean, we're talking about the same core idea powering systems that can do all these different things, from spotting a tiny butterfly in a photo, to cleaning up a fuzzy image, to recognizing birdsong in a forest, and yeah, even driving a car down a busy street. And hey, this isn't even a brand new idea. A groundbreaking project called Alvin did this decades ago. It was a vehicle with a simple camera and a neural net that literally learned how to steer itself just by watching a person drive. It was an early and seriously powerful proof that this whole concept works. So let's zoom out. What's the really big takeaway here? The crucial thing to understand is that this isn't just about building better gadgets or faster computers. By learning from the brain, we're watching a whole new kind of science emerge, one that blurs the lines between biology and computer science. What we're really doing here is decoding the fundamental principles of biological intelligence and then recoding them into artificial systems. We are building machines that don't just calculate, they perceive, they act, and they adapt to the world around them. This whole approach actually helps solve a deep puzzle that was posed by the legendary computer scientist John von Neumann. He couldn't figure out how an imperfect, messy network like the brain could be so reliable. And the answer seems to be that principles like sparse coding create representations that are so robust and efficient, you just don't need perfect wiring for them to work incredibly well. And that leaves us with one last fascinating question to chew on. If a few powerful, elegant principles, like sparse representation, are enough to build systems that can see, act, and learn, does that mean the fundamental blueprint for intelligence itself is actually far simpler than we ever dared to imagine?